All right. Happy Thursday. Thursday, week 5, I believe. Okay. So this section is probably the one that the students gives gave prior students the most trouble. It's also one that I use quite frequently. So I'm going to give you an example of how I use this to show that a student was cheating. Um, I had a student that got missed 1 out of 35 on a multiple choice test. They told me that because they finished the test, it was like 35 math questions in less than 6 minutes. And this was math that should have required work. It was a multiple choice on the computer. They missed one. So I called them on it and I told them that I felt like they were cheating and I wanted to talk to them about it. I knew they were using photo math. They said, "No, I guessed on every single question. I just went through and guessed on every single question." So I used the math that you're going to learn today to calculate the probability that they could get 34 out of 35 with guessing on every single question. And it ended up being like 3 in 100 billion or something chance that they would get 34 out of 35 using the math that you're going to learn today. And so by showing them that probability, they kind of backed off and said, "Yeah, I used photo math and I made them redo the test." But I use this a lot, and it's most of the time it's not for anything useful. It's just because I'm a super curious person. And if I know math that can give me numbers, then I'm going to do the math. And I always have a fancy schmancy with me. And this is really good fancy schmancy math that we're going to learn today. So we're going to talk about binomial experiments. You're going to learn what a binomial experiment is. And then we're going to calculate some probabilities with binomial experiments and the mean and the standard deviation. And I'm going to show you the graph of the binomial probability distribution, which you're not going to have to graph them, but I'm going to show it to you because I'm always showing you graphs. So that's today. I'm going to kind of show you when I'm talking about what a binomial experiment is, I'm going to kind of show you why it's a good idea to use your calculator because the math that would be required without using the calculator is super overwhelming. So I'm going to kind of show you what's going on behind the scenes. I love doing why, answering the why question, or the why does this work? I love those questions, or why do we use this, or why do I need the calculator? I love all of that. I love the how things work part. I mean, I have so many books on my bookshelf about how things work. It's just the way my brain is. This is part of the reason I majored in math and not English. Even though I started off as an English major, someday I may tell you that story. Anyway, here we go. So I'm not going to ask you to retell me the criteria for a binomial probability experiment, but it's when you're taking your test or when you are doing your homework, it's good to keep these in mind, the criteria for a binomial experiment, because it's going to let you know when to use this calculator function. So these are kind of the things that you're going to ask yourself. Plus, final project if you end up using categorical data rather than quantitative data, using a binomial probability experiment might be useful. Okay, so there has to be a fixed number of trials. So every repetition of the experiment is called a trial. So rolling a dice or maybe figuring out how many M&Ms or how many bag M&Ms, green M&Ms are in an M&M bag or whatever. However many times you repeat it is the trial. However many people you chose, like my sample size, if I chose 20 people out of a population, I would have 20 trials because each person would get to like answer whatever the question is. So fixed number of trials. Next, the trials have to be independent. We talked about independence in the last section. Was it the last section or the last unit? I believe it was in chapter 5. We talked about how we know trials are independent. So the outcome of one cannot affect any of the other trials. So rolling a dice is a really good example of that. So for each trial, there has to be two mutually exclusive outcomes. Now, rolling a dice, clearly there are 66 different outcomes, but basically it has to be success or failure. So I just like rolling a dice because it's something we all easily can think of in our head. So if my event is rolling a three would be a success. Rolling anything that's not a three would be a failure. That makes sense. So those are the two different outcomes, a success or a failure. And if I can roll a three or not roll a three. There's no other answer could possibly be a three. Three is disjoint of one, two, four, five, and six. Plus, our probability of success is fixed. So there's a fixed probability. So this is like, for example, in your homework, there was the vaccine problem, and it was like some of you got like 38% of the people were vaccinated. So that 38% would be your fixed probability. So every random person I pull out of the population, each person, I have a 36% chance of getting somebody who's vaccinated. So it's a fixed probability. Any question about any of these? All right. So that's a binomial probability experiment. Okay. So here's the notation that we use. We use lowercase n for how many trials we have. P is the probability of success. 1 minus P is the probability of failure. So if I have 38% chance somebody is vaccinated, that's a 62% chance they are not vaccinated. So the probability of failure would be 62%. The capital X is our binomial random variable. And I'm not going to be mad at you if you use a lowercase x. I'm not going to really notice because lowercase and uppercase look the same. But the capital X is the variable. And so all of the outcomes of the variable would be your X or success or failure. So, our number of successes is right here, is the lowercase x. So I'm saying that my number of successes is going to be somewhere between 0 and the number of trials that I have. So X is the number of successes. And it's going to be really helpful when I'm showing you the calculator function on how this works. Okay. So, oh, see, this isn't supposed to show up. Okay, it's okay. I meant to make it not be here and for us to guess, but it's okay. We already have the answers there. So a player rolls a pair of fair dice 10 times. The number X of sevens rolled is recorded. So I have 10 trials. This is my fixed trials. This is my probability of success is also fixed because my probability of rolling a 7, so this is a fixed probability. So fixed probability. And what was the last thing? Oh, obviously the trials are independent. So let's take a look at the next one. Okay. I wish I wouldn't have had the answer on here, but it's too late now. So the 11 largest airlines had an on-time percentage of 84.7% in November 2001, according to the Air Travel Consumer Report. In order to assess the reasons, this is supposed to say X for delays. I don't know. Reasons for delays. An official with FAA randomly select flights until she finds 10 that were not on time. The number of flights that need to be selected is recorded. All right. So this is actually, you don't need to write this down because we're not learning this, but this is called a geometric probability. And I think this is chapter 11 or chapter 12 in our book. We don't go that far. If you end up going to Math 244, which is the class after this, or Stat 244, they will talk about geometric probabilities. But there's not a fixed number of trials because we keep drawing, we keep choosing flights until we get 10. We could end up with 35, 40 flights. We could end up with 150 flights. We don't know. There's not a fixed number of trials. It does have an on-time percent of 84.7%. That's a fixed probability. And we're assuming they're independent, which I don't really think they really would be independent if it's, oh, it is because it's not all at the same airport. So it's not all at the same airport. It's all flights. Um, so not likely to find ones that affect each other, but there's not a fixed number of trials. Therefore, this is not a binomial experiment. All right, moving on. In a class of 30 students, 55% are female. The instructor randomly selects 4 students. The number X of females selected is recorded. Okay, the trials are not independent because if I have 55% females, let's just pretend I have 100 students in the class, okay? Even though it says 30, but 100 is an easier math for me. So once I take one student out, let's say I take a boy out. Now there's 99 students in the class. So now I have 55 females, but I now have 44 males instead of 45 males. So the probability of success is now different. So the trials are not independent because it affects the probability of pulling a female next time. So it's going to be slightly more. So you see 55 divided by 99. Now it's 55.6% are now female. And then if I pull another one out, let's say I pulled another one out, another male out. Now it's 55 out of 98. Now it's 56% are now female. So that it's the trials aren't independent because it affects the probability of getting a female the next time. So what I would have to say is like 55% of students in the US are female. If I'm randomly selecting 4 students from the entire US population of students, now those are independent. Because choosing 4 students out of the entire US is not going to change significantly enough that probability to affect anything. All right. Okay. So we're going to construct this is kind of the why behind. So let's go in our Wayback Machine and go back to the last unit, so unit 5. We talked about the outcomes of the experiment. So remember when we were talking about flipping coins, and my flipping coins, 2 coins. This is really ugly, but my writing. So I could get heads, tails, tails, heads, and tails, tails. So these 2 things are different. So I have 2 different ways to get 1 heads and 1 tails. There's a method to my madness. So think about if I'm looking at more things. So I'm looking at a sample size of 4 of Americans and whether or not they have type O blood. So let's take a look at the different outcomes that you can have, and it gets crazy big. I'm going to create I don't know why I can't speak. I'm going to create a tree diagram, and you're going to see that this gets really big really quickly. So take a look here. Okay, so start off my first trial. I can have a success or a failure. Coming off that success, I can have another success or another failure. Or coming off this failure, I can have another success. I can have a success or another failure. And then off the next ones, I can have success or failure on each of them. So take a look here. I have one way to get 4 successes and one way to get 4 failures. Let's see, here's 4 failures. Here's 4 successes. So I have 1, 2, 3, 4 different ways to have 3 successes. And I have 1, 2, 3, 4, 5, 6 different ways to have 2 successes. So you see how many different ways that we can have successes and failures? This would require a lot of math for us to calculate probabilities with all of these different ways to do this. I'm going to show you on the next screen what that's going to look like. Okay, so take a look here. So we talked about So the probability of getting 0 successes, there's one way. And so in order for there to be 0 successes, I have to have failure on one and failure on the second and failure on the third and failure on the fourth. Remember, with and probabilities, we multiply. So I have probability of failure times failure times failure times failure. There's a 7% chance of success. There's a 93% chance of failure. This one is pretty simple because I'm just basically 0.93 to the fourth power. And I have 0.74805. Okay, that's all lovely and good. So there were 4 different ways to get 1 success. So we go back here. There's 1, 2, 3, 4 different ways to get 1 success. So to get 1 success, I have 3 failures. So that's the 0.93 to the third power 4 times and 1 success. So 0.2252. So the thing about this is that if you were doing one of these binomial probability distributions, if you were doing one of these binomial probabilities, you would have to determine first how many successes and how many failures we have, how many ways to get 3 successes. So imagine if I was saying we were doing 15 trials. Think about what that tree diagram is going to look like. It's going to look outrageously huge. So in your brain right now, you should be saying, I am so thankful that there is a calculator function for this, so I don't have to create anything like this. I'm not going to make you create a tree diagram. It would be huge and no fun, and nobody wants to do this. So I'm not going to make you. So, all right. So let's move on. We're going to get to the calculator function in just a moment. Okay. I am also not making you do combinatorics, which is this right here. So don't worry about that. I'm not even going to teach you how to do it because it's using the Binom PDF and the Binom CDF is so much easier. I love combinatorics, which you're sitting here going, I don't even know what that word means. Is that even English? Yes, it is. And it's beautiful and it's fun and it's great. And if you were in my AP stats class at the high school, I'd probably make you do it. But this isn't AP stats at the high school. This is stats 243 at RCC. And you absolutely do not have to do combinatorics. So the way that we're going to calculate is using Binom PDF right here. I will tell you how to get there and how to use it in a minute. So this right here is the number of trials. This right here is the probability of success. And this is here is number of successes. And this is for exact. I'm going to write exact, and you'll understand in a minute. So if I want to know exactly, so if I say, like, if I did 4 trials, randomly selected 4 people from the US, what is the probability of getting 3 of them with type O blood? I would use this to calculate that. And it's so much easier than figuring out how many ways can I get 3 people with type O blood. This is so much easier just using Binom PDF. And this is for an exact number of successes. So exactly 3 people with type O blood is what I'm looking for. Questions so far? Okay. We're going to do some examples and it's going to hopefully all make everything clear. Okay. So math symbols, I'm going to whip through this really quickly. This is a good, sometimes we forget things. And so I just put these math symbols here. If you printed out the PowerPoint, this is good for you remembering more than, at most, less than, all of that. This is just a good reminder of what the symbols look like. So I just threw that up there. Moving on. Okay. According to Experian Automotive, 35% of all car-owning households have 3 or more cars. In a random sample of 20 car-owning households, what is the probability exactly 5 have 3 or more cars? Okay, so I'm going to show you how to do it in the calculator in just one moment. So remember, I'm going to put the binom, PDF, and then it is number of trials, probability of success, number of successes. Okay, so what this is going to look like, binom, PDF, my number of trials. I took a sample of 20 car owning households. Probability is 35%, so it's 0.35. And then exactly 5. This is what we're going to put in our calculator. So I'm going to bop over to the calculator in just 1 second. Let you write that down first, and I'll bop over to the calculator. Okay. Okay, so notice above this VARS button right here, it says DISTR. So this is for distributions. So we're doing a binomial probability distribution. So right above VARS here is distributions. So I'm going to do second VARS, and it's going to bring this lovely screen right here. Okay. I'm going to scroll down to letter A, binom PDF. Yes, letter Z. Oh, I didn't realize this was showing. So yes, the second one is binom CDF. That's not what we're looking for. We want binom PDF. You want A and hit enter. So our number of trials, it's 20 because we have 20 people. We're randomly selecting 20 car owning households. The probability that they own 3 or more cars is 35%. That's a 4. And I just put 0.35. There we go. And then the number of successes I'm looking for, I want exactly 5. Exactly 5 have 3 or more, cars. So trials, probability, X value, hit enter. So if your calculator doesn't have that screen where it lets you put stuff in, this is what it's going to look like. This is just the way that I wrote it down. So you can just put them in with the parentheses, hit enter. Let's see. A second, I'm going to write this down. Okay. So we have the probability that the value that our successes are 5 is 0.127 or about 12.7%. So there's about a 12.7% chance that if I took a random sample of 20 car owning households, that exactly 5 would have 3 or more cars. Questions before I give you more? Okay. Here it is right here. Don't even worry about the combinatorics part. We're not doing that. Don't worry about that. Okay. Now, sometimes we want something different. So sometimes we want a range of values. So in a random sample of 20 car owning households, what's the probability that less than 4 have 3 or more cars? So I'm going to give you a visual here. So I'm not going to do it all the way to 20. So I'm looking for either 0, 1, 2, or 3. I want this group, this range in my answer. What's the probability that either 0, 1, 2, or 3? So I want to know the probability that X is less than or equal to 3. Correct? That's what I'm looking for. So instead of using binom PDF, we're going to use CDF. This right here means cumulative. And I was going to write that, but I'm having issues. Cumulative, which means I'm adding the probabilities of 0, 1, 2, or 3. Because remember, with or, we add. So I'm finding the probability of 0, the probability of 1, the probability of 2, and the probability of 3, and I'm adding them all together. So what this is going to look like, number of trials, 20, probability 0.35, and then number of successes, so it's 3 or fewer. So I'm going to put 3 right there. So less than 4 is the same thing as less than or equal to 3. I'm going to write this right here. So let's put that in our calculator. Put that on the other page there. Okay. So once again, second vars. I'm going to go all the way down here. Now we're going to go to B. So once again, number of trials is 20, 0.35, and we're using 3 or fewer. So I'm going to put 3 right there and hit enter. So about 4.44%.
My calculator just, when I do the binom CDF, it just gives me trials P X value. Is that what I'm supposed to have?
Yes. Want me to go back in there?
Yes.
Because it's a range, just like mine. Is that what yours has?
Yeah. Yeah. Yes. Thank you.
So the X value is the top, so like 3 or fewer. So it's just how high does it go? We don't have a greater than or equal to button, but we do have the less than or equal to, so we'll have to adapt. Okay, so I'm going to go back to my screen here. So this is what we got rounded to this. So the way that I remember it, because my brain, I always need some mnemonic device. PDF, I think of this as precise. That's not what it stands for, but that's why I need to think about it to remember it. And then CDF is cumulative, which is really what it stands for. But this is just how I remember it. Precise is for exact. If I need the exact number of successes, precise. P is precise. Cumulative, I need to add it all together, add it all up to whatever, however high I'm going. So cumulative and precise. This is just how I have to get my brain to remember it. If you don't need those mnemonic devices, you can throw it out and ignore what I'm saying. I'm okay with that. You take what you like and throw the rest away. Okay. So this would be unusual. So since the probability is less than 5%, this would be unusual. We're sticking with that. We're not going to ever throw that away. If something happens less than 5% of the time, it is considered unusual. By the way, I did finish grading the hand and homework number 4 today. I was so impressed with how many perfect scores there were. This class is absolutely amazing. You guys are great. Good job. Okay, moving on. Now, this is where y'all are gonna be mad at me. This word right here. This 2 words, whoa. These 2 words right there. Every time you see the words at least, you will use the complement rule. Once again, every time you hear the words at least, use the complement rule. There you go. I'm going to say that 5,680 times in this class. Just remember, every time you see the words at least, you will use the complement rule. So we want to know what the probability is that at least 4 cars will have at least 3 homes sorry, at least 4 homes will have 3 or more cars. I'm going to draw a visual again.
The complement rule, for some reason, I wrote this on 2 separate pages in my notebook, and I usually keep everything together. The complement rule, isn't that the 1 minus the number with the exponent?
Yes.
Okay, so I need to combine those. I don't,
It's because we've addressed it about 3 different times in this class. That's probably why you have it in a couple of different spots. Because I had it in I had it in chapter 5, and then I think we used it on Tuesday also. So I think that's probably why you have it.
okay, thank you.
So at least 4. At least 4 means these, right? I want to know the probability of all of this, of one of those being true, which means I want the probability of not this, right? So if I'm looking for 4 or more, I'm looking for not 0, 1, 2, or 3. So I'm going to look for, so the probability, stop it. Probability that X is greater than or equal to 4 equals 1 minus the probability X is less than or equal to 3, if that makes sense, because it's not 3 or less. So therefore, in my calculator, I'll put 1 minus binom PDF 20, I couldn't remember how many trials, 0.353. I hope that visual helps, that if I'm looking for this, then it's not the other, then it's not this.
So do we just get the number for binom PDF and then -1 from it once you have that number?
You can do it either way. You can do it either way. So for example, if I wanted to, I'm going to get out of here because I already have the 3 or fewer right there. I can do 1 minus and then bring that answer. I can do that if I want to, or I could do 1 minus and then go second binom CDF. Trials were 20, 0.353. And then I could do it that way. Either way is fine. However you want to do it.
Okay, thank you.
Yes. You have all the good questions tonight. You are on it. Good job. Okay. So we got about 95.56% chance that 3 or more, or at least 4 have 3 or more cars. All right. Any other questions before we move on? Okay. I'm going to have you guys try this on your own. I'm going to give you a few, one of each set, and then one tricky one that you can try if you want, or you can not try. All right. I would like you to do A, B, and C for sure. And if nothing else, think about how you might do D. Think about a strategy you might use. So go ahead and try A, B, and C. So 41% of all households are wireless only households, and a simple random sample of 20 households. Look at these three different probabilities. Go ahead and do those in your calculator. I will work quietly behind you. I'm not going to do D yet, though.
If you type in the number to the wrong place, will it just tell you error? Like,
Possibly. It depends on what, I mean, if you swap 5 and 20, Is that what you're
Yeah,
talking about?
yeah, probably.
I don't know. It might. Let me give it a shot. I
Cause
don't.
I'm like error. Well, I guess that's good that it tells me I did it wrong right away.
Oh, it did. Mine just gave me 0.
Okay, then maybe we'll see. Thank you.
How'd we do?
I don't know. It's not letting me type in any number like in the Binom PDF, so I'm still I
Okay.
have no idea.
So let me jump to my calculator. So Binom PDF is where are you sure that you're in Binom PDF?
Yes,
Okay.
yes.
So it should be 20,
Yes.
0.41,
Got it.
and then 5.
Five.
Yes.
Yeah, and then I hit yes and then enter. Of course.
Is it
All
working
good.
now?
I got it. I got it. Yeah, but I don't know what it was. I
It
had.
happens all the time. It's kind of like when you take your car into the mechanic and then it quits making that noise
Oh my God.
thing,
Okay.
right? It's all right.
You.
I'll give you a second to get these other ones.
Will you go back to the PowerPoint?
Yes. Sorry.
No,
No,
you're
you're good.
okay.
All right. So I'm hoping that the rest of you, I know Hannah was having some issues, but I'm hoping the rest of you thought about a strategy for letter D. So I'm going to do a visual on this one again. I'm not doing all of them. So what I'm looking for is this right here. That's what I'm looking for. I'm looking for that right there. So we do not have a greater than or equal to for binomes, PDF or CDF. We don't have a greater than or equal to. All we have is a less than or equal to. So therefore, if we're looking for something that's a range like this, like 5 to 7, what we need to do is we need to find this right here, 7 or fewer. And then I'm going to need to subtract off this right here. That's ugly. I don't like that. I'm going to make it a different color. I'm going to subtract off this right here. So what I need to do in this case, and I'm pretty sure that there's one in your homework like this. I don't think I give you anything like this on the test, but there is one in your homework like this. So what I did was this binom CDF 20 0.417 minus binom CDF 20, 0.414. So that's subtracting off this piece right here because I'm figuring out what that probability is and subtracting it off. So I'm going to put that in my calculator. I'm going to pop over and put that in my calculator so you can see what that looks like. Clear all this up first. Okay. So I'm going to take binom CDF. There's 20 trials still. 0.35. We're going with 7 minus back there. 20, and then we're doing 4. So I could subtract that off. And then just hit enter, and that gives me my answer. So about 0.4, so about 48% of people have about 48% so the probability, sorry, I'm like losing my mind. The probability of getting between 5 and 7 people in a random sample of 20 that are wireless only is about just under 50%. Questions?
I missed, why did you do the probability of success at 35.35 instead of 0.41 on the calculator?
Because the last thing we did was 0.35. The thing before that was 0.35. It was for no good reason. Let me fix this.
Okay, it was supposed to be 0.41.
It was supposed to be 0.41, but because
Okay.
I was thinking about the previous example, there we go. Okay, so it's 33.8. This is why I keep you around. Thank you so much. I'm glad y'all are finally feeling comfortable calling me on my errors. Could tell we're halfway through the term when you all start calling me on my errors. Thank you for that. All right. Now that I have the right numbers in there, hopefully you all got the same thing as me now. Other questions? Okay. Let's move on to our next piece then. Okay. So once again, binomial, we're going to do mean and standard deviation. There's like 12 different formulas, unfortunately, for mean and standard deviation for these binomial or for through the whole term. So you remember we did mean sub x? That was on Tuesday. We're still doing mean sub x, but this is a capital X. The last one was a lowercase x, and I know you can't tell the difference, but it's okay. So the way that we calculate the mean or the expected value is just the number of trials times the probability of it happening. And it makes total sense. If 41% of the households are wireless only households, you would expect 41 out of 100 to be wireless only. So it absolutely makes sense that that's our expected value. Standard deviation is a little bit different. So for the standard deviation, we take the square root of the number of trials times the probability of success times the probability of failure. And this is our standard deviation. So NP times 1 minus P. So square root of number of trials times probability of success times probability of failure. So that's how we do this. Okay. So for the Experian Automotive car owning households, in a simple random sample of 400 car owning households, we're determining the mean and the standard deviation. So the mean for our mu sub x, it's going to be 0.35. I'm going to do it the other way because I'm going to do 400 times 0.35. 400 times 0.35. So we would expect 140 out of those 400 to have 3 or more cars. So for the standard deviation, so my sigma sub x, we would expect 400 times 0.35 times 0.65, which is your probability of failure. So you can put that whole thing in your calculator. You might need to be nice with parentheses. So my standard deviation is approximately 9.54.
And where'd you get the 0.65?
1 minus 0.35.
Oh, okay.
All right, other questions? All right, let's put this to use. So this is important. And I know this doesn't seem important, but this is important. You're going to be asked this. I believe on your next quiz, you are asked this question. For a fixed probability of success, as the number of trials increase, the probability distribution becomes more bell-shaped. It does if, so on your quiz, when you answer the question, I believe that it specifically says, under what circumstances does it become more bell-shaped or something like that. I want to make sure you put this in there. It becomes bell-shaped as the number of trials increases if NP times 1 minus P is greater than or equal to 10. So this is if the number of trials times the number of successes times the number of failures is greater than or equal to 10, then we are bell-shaped. This becomes really important because most of our tools that we use for analysis require that our distribution be bell-shaped. So we test this with the NP times 1 minus P greater than or equal to 10. We test to see that it is bell-shaped before we apply our methods of analysis. So this right here is our rule of thumb. This is what we use. So on your quiz, this week's quiz, when it asks you about that, make sure that you state the NP times 1 minus P must be greater than or equal to 10. However, whatever your wording is, if you're including that, I will say, yes, good, we're good. Now, if you Google this, or if you try to have AI do it, which some people do on their quizzes, they Google or they use AI, it will give you a different answer because it is thinking of broader cases. This is very specific case. The Google answer or the AI answer will be including broader cases. So you probably will lose points if you're using Google for it, which I know none of you would ever use Google for your quizzes. You would never, ever do that because you know you're not supposed to. I'm just giving you a for instance. So make sure that you use this and yeah. All right, moving on. So our empirical rule, we already kind of talked about this. Empirical rule states that 95% of our observations are within 2 standard deviations of the mean. We use the 2 standard deviation rule to find outliers. So if an observation happens less than 5% of the time, it's considered unusual. Y'all know this. I just saw your hand in homework. Y'all know this. Y'all got this. Okay. So according to Experian Automotive, 35% of all car-owning households have 3 or more cars. A researcher believes that the percentage is higher than reported by Experian. So he took a random sample of 400 cars, 400 car-owning households, and he found that 162 had 3 or more cars. He wants to know if this result is unusual. There's a couple of different things that you can do. You can either use Binom CDF, Binom PDF. You can use one of those, or you can find the Z-score of 162 cars, or you can find the where the upper limit is. using two standard deviations. I'm going to use z-score just because it's fun. So remember the z-score is x minus mu over sigma. So I'm going to do 162 minus 140 over 9.54. I'm going to put this in my calculator. Don't forget the parentheses in your numerator. Don't forget those parentheses. I got a z-score 2.3. That is more than 2 standard deviations from the mean. Therefore, it is unusual. I'm going to do this another way. Just so I'm going to move this because I can. I'm going to do this another way. So you're more than welcome to do this however you want. But for example, if you did this on a test, I want you to tell me which method you used or show the work so that I can verify. You could say binom PDF 400 point, 0.35 162. So what is the probability of getting exactly 162 if the probability is 35%? So I'm going to do that right now. 400 trials. See, this is where that 0.35 came from. I got a probability, whoa, of throwing my pencil. That probability is high. I think I do that in every class, don't I? I throw my pencil somewhere. My Apple pencils. I got approximately 0.003. So that is definitely less than 5%. So that's another way to do that. The other way, because, you know, you've got to do all the ways. The other way would be 140 plus 2 times 9.54. That is my 2 standard deviation rule. That would be my upper boundary. And since 162 is higher than 159.08, it would be unusual. Questions about these 3 methods or anything with this problem?
So if you were going to ask this on a test or quiz, you wouldn't provide us with the mu and the standard deviation though, would you?
No, you would
have to figure that out. Okay.
or you could just do this. That's probably where I would go. I would probably just jump to binom PDF because it's less work. I didn't mean the mean and the standard deviation, but your homework, my open math is going to ask this question more than one way. And so I wanted to give you all of the tools. Good question. All right. I would like you to try this one, whatever method you choose. So, in a simple random sample of 300 households, oh, this is 41%. This is the 41% are wireless only. That's really ugly. I'm going to rewrite it. Okay. So I would like you to calculate, would it be unusual to have exactly 143 that are wireless only if I had a simple random sample of 300? Whichever way you want. I don't care if you do the mean and the standard deviation. If you want, go for it. You can use binom PDF, use whichever method you choose. I will calculate, though, the mean and the standard deviation. Did anybody get an answer?
Yes, it's unusual.
Yes, it's unusual. Do we agree? So, what method did we use? Anyone have a method that they used?
The binom PDF.
That's usually where I go also. To me, that's the least amount of work, and I am kind of lazy. So we have 300 trials, 0.41, and then 143. And I did 400 trials in my calculator. What the heck is wrong with me? I'm going to change that real quick. So I got, 0.003. Is this what you got?
Yeah.
Yeah.
Yeah. All right. So that works. Another way is we could have calculated the z-score. Whoa, that was weird. Okay. So using the z-score, I would do 143 minus 123 divided by 8.52. My cat is currently scratching my leg because she wants to play. The z-score of 2.35. Yeah, that's unusual. Or you do I'm going to use a different color because this is what I do. Do 123 plus 2 times 8.52. Gives me 140.04. That was my upper boundary. So anything above that is an outlier. So there we go. All three methods, it shows that it is unusual.
Wait, can you cover how from the binom PDF, how we know that it's unusual with the 0.003?
That number is less than 5%. So
Okay.
so if you get a probability that is less than 5%, it is considered unusual.
Where did the 41% come from?
That was from previously, way back here when we did the cell phone thing. Where is it? Right there.
Oh, okay, thank you.
No problem. Let me go all the way back. Uh-oh, there we go. Anyone else? That is the last slide. That is the last of the information that I have for you tonight. So, questions while we were still recording about this or anything else?
I had more questions, but I just really I need to write them down. I might just email you or something because I feel like from the 5.1 to all the way through like all of the fives and then now with the sixes, I don't know, my brain's saying no. So I'm gonna gather my questions and make it make sense.
Okay.
So
Absolutely. Yes. Send me a message or an email. I'm happy to help you. I want this to make sense. 6.2 seems to be a big sticking point for a lot of people. And most of the time they leave the class being like, oh yeah, this isn't too bad. And then they'll start doing the homework and be like, I have no idea what's going on. So I'm completely happy to answer any questions you have. I am here for you guys. I want you to succeed. And that first test tells me that I'm going to probably have a record number of A's this term. So excited about it. You're all doing so great. All right, I'm going to turn the recording off and then anything else you want to ask, you may.